All right. My camera's not recording, but the Camtasia's recording, but it's recording screen and webcam. That's right. That's good. Highest N level electron.
D is higher, it's still 4s.
Right. It's still 4s. Why is that? So this is drawing this diagram should be very easy, but answering these questions are going to be the next level of difficulty. The next level of difficulty would be the valence electrons, and then why is it? Can somebody remind me why I said that is?
Because the oxidizer can only take off as much at all, or like
Not exactly. It has to do with the oxidizer. Does somebody remember? This is, I got a lot of questions about, how better to prepare for the test and this kind of stuff. I think the most important thing is just to be able to do the simple stuff like this. If you can do the simple stuff, then have that mastered. Then you can start thinking about the more difficult stuff. The more difficult stuff is the challenge questions that they have. But you want to get the basics down, where you don't have to think about it. I mean, it should be simple. This like drawing a diagram like this should be very simple. These are easy points. However, I might ask you, you would think that this would be like a question you might expect, like at UCLA. You might think the 3D will be the valence here. Why aren't they? And so you'd have to explain it in some short essay. What would you say? That's what eventually you want to get to. Eventually you just want to be able to get the simple stuff that's mindless. You don't have to think too much about it. It's just drill, 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 and then start thinking about the more advanced. But that's not even more advanced because I already talked about it in class. Usually the stuff that challenges you, they don't talk about in class. It's not in the homework. And so it's something you really have to think about. And those aren't so easy to do, but if you have the simple stuff down, then those are more feasible. It's not like you're always going to get it, the challenge problems.
It's the outermost?
But you don't have to get the challenge problems to pass. What's that?
Because it's the outermost?
Yes, exactly.
The valence are the outermost, and the core ones are the ones that are inside.
Yeah, right. And so this is odd. It has two valence electrons, but once you lose these two, then we have vanadium 2+. And then these become the valence after these guys leave.
There's 2 plus and 3 plus.
For vanadium, 2+, 3+, 4+, and 5+. And so 2+, these guys leave. 3+, 4+, 5+, we pluck these off in succession. Now it gets more and more difficult. The higher the positive charge, the more difficult it is. This is called ionization energy. The weird thing is you think these highest energy electrons would be the easiest to pluck off, but sometimes the highest energy aren't the easiest to pluck off. Right? Sometimes these ones are the outermost. Even though these are higher in energy, these ones get plucked off first because if you're the oxidizer, you want to get the outermost electrons first. And so when we think about ionization energy, which was the topic we left off last time, there are different levels that we learn ionization. So first you want to do the simplest level and just worry about that. And so this is the way you should study, because if you try to do everything all at once, it becomes overwhelming. So what you do is you just do it in little baby steps is the best. If you do it in little baby steps, then what should you know about ionization energy? What did I say about ionization energy?
It's easier way to work.
I just gave you a very, very simple way of understanding ionization energy. The very simple way of understanding ionization energy is the smaller the atom,
The more degree has,
yeah, and the bigger the atom,
the easier it is to get up.
yeah, good. And so that's at the basic level. Once you get the basic level down, then start thinking about the more complex things that happen in ionization energy. The more complex things were the blips. Remember I talked about those blips and I told you to ignore the blips for now? I told you to ignore the blips because it's too much. to do it once. This is why cramming is kind of ineffective, because cramming is like, if you cram right before the test, then you've got to learn everything. You can't take little steps and learn it. And so what you want to do is you want to take little steps and get the basics down and then start digging deeper into those types of things. And so I think that's one of the tips I'd go, if you're looking for tips to study. I know some people were asking about that. And so little things like this, little things that I mentioned. So this is vanadium. Chromium's weird. What happens with chromium?
Chromium, one of the 4 S's will do.
Yeah, good. Chromium should look like this, but one of the 4 S's go over here. Right. After chromium comes
Manganese.
manganese. Manganese is just normal, like this. Right. And so manganese is +2, +3. It's +2 because we lose a 4s here. And then +3 if we lose one of these. Now this is half filled, so you might expect some additional stability there, being half filled. But we can see for iron, iron is going to add one more electron. Which one should I pair up here? Doesn't matter, so we'll just pair up the first one here. And so you can see that iron is going to be +2 or plus, not +4, +3. +2 and +3 are the most common charges for iron. And +2, we lose these 4s electrons. +3, which one of the d electrons will we lose?
You want me to remember the extra?
Okay, name this electron for me. I don't want to know. I don't want you to point to it. I want you to tell me the name of that electron.
B20 spin down. B20 spin down.
Oh yeah. What's spin down called?
South.
No.
-1/2.
-1/2. Yeah. 320 -1/2. We don't call it 20 because there is an L = 20. Did you know that? There's an L = 20. That's possible.
Oh, I said 320.
I know, you don't want to call it 320 because people will think you're talking about the 3N, the 20L. L = 20 exists.
Oh, I see.
Yeah, although it would be forbidden in this case.
So I would say like N4, L 320.
No, you just say 320 because 20 is implying that we have 3 numbers, N, L, M. So if you say 3 and then you say 20, I would expect L to be 20 and then I'm waiting for one more number. And so, yeah, right, exactly. Except this would be a forbidden. What N value would we have to have to see an L = 20? 21, good. And so then we would have an L. So we could have a 21, 20, and then it could go -20 plus 20. So the total of 41 orbitals.
L is equal to N - 1 again, right?
Max. Yeah. And so if I'm in the N = 21, then L = 0, 1, 2, all the way up to 21 max. And so all those orbitals will exist. And then to figure out the numbers, we have to figure out the M values for those. And so this is why I say, don't say 20 because somebody might imply. You would say 3, there's 3 separate numbers, so 320 would be it. All right, so that's a little bit tricky with the valence electrons. Especially in the 4th shell. In the 3rd shell, the 2nd shell, the 1st shell, it's straightforward. You don't have this complication with the Ds. The Ds are thought of as inner shell electrons here. And so there are a whole bunch of things that happen. So as far as size goes, if we go to hydrogen and then we go to helium, what's the smallest atom on the periodic table? Helium. And then it grows bigger, so. What's the biggest atom?
FR, whatever that is.
Yeah, FR. A lot of people don't do FR because FR is radioactive. And so it doesn't have a very long life. So rather than FR, people do
CS.
CS. Do you know what CS stands for?
Cesium.
Cesium. Cesium's biggest non-radioactive.
What's the name for FR? What's it?
Francium.
Francium?
Yeah,
Francium?
francium.
I know for like California and Moscovium as well, right?
Mm-hmm. Right. So, because of this, when we think of ionization, you know, the 3D do not get ionized first. So when we do the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. Some information is lost here. So what some people do is they, rather than combining all the p's, they separate it. And so, for example, they might go 2px2, 2py2, 2pz2. You could do something like that. And the same thing with the 3p's. You could expand these out to 3px2, 3py2, 3pz2. And then the 3Ds, we can also expand these out too, because we have the 3D. You don't need to know the designations, but we could say 3dz squared 1, 3dx squared minus y squared 1, 3dx y 1, 3d yz, 3d xz. Those just refer to planes. This is the nomenclature that they give. And so those 3 electrons are spread out over 3 of the Ds, and it doesn't matter which of the Ds you pick, but that's expanded out. Or we can contract it down. You know, if we contract it down, then we probably fill to argon here. And so if we fill to argon, then it's a 4s2, 3d3. Now, because of ionization energies and distances, because we're looking at the reactivity, metals tend to lose electrons. And so we want to see what the common charges for this are. And if that's the case, we reverse this order here. So it goes 3d3, 4s2. And so I call this the filling order here. And down here, I call this the losing order, or the ionizing order. So if you're an oxidizer, you come along, you're not going to pluck the 3Ds. You're going to pluck the 4S. Why? Well, I had said why. It's the, can somebody repeat it? This is the other thing. For the test, it's a lot of like, a lot of just what they call recall information. And usually recall problems are easy points. But if you never got the information, you can't recall it, and therefore it's impossible points. And so the more stuff you can recall, the better, your base. And so you want to be able to just recall, like, it depends on what the cutoff is. The cutoff for this class is 65% is a C. So you want to at least be able to recall 65% of the information or something like that, and that gives you a good chance. But it's tricky because at UCLA, a lot of the classes that I took there, they had like 4 questions on the test, each worth 25 points. So if you miss one question, you're already down to 75%. You miss 2 questions, you're already down to 50%. And so,
Wait, a C is a 65?
In this class. In most classes, a C is what? 70%, right? And so you want to be able to recall that. Now, it's difficult to recall that unless you, and this is why when I was in high school, my geology teacher always said this, if you want to get straight A's in college, learn shorthand. Because if you learn shorthand, then you can write extremely fast. And if you can write extremely fast, you're going to be able to capture close to 100% of the material that was covered. And then you should be able to recall that if you try to memorize it. Memorizing this stuff isn't so easy. I was listening to a talk. The dean of the medical school at Stanford was talking about when he was a student, and he was taking organic chemistry. in organic chemistry, there's a ton of memorization in organic chemistry, and that's why it's one of those classes that tends to weed out a lot of students because of the amount of memorization that you have to do. It's not all memorization. There's a lot of stuff that you don't necessarily have to memorize. But he was saying he had a photographic memory, and therefore organic chemistry was so easy for him. And I thought, wow, that's pretty impressive. He said his photographic memory is faded, but then I thought, that's it. If you could just recall stuff. You don't have to come up with some kind of brilliant problem-solving method or some super challenging problem. It's just a recall of information. And that's what I said earlier. I said that for most of the tests at UCLA, if you can recall 90% of the information, not 90%. If you could recall the information, then 90% of the test was recall. Just, do you remember it or not remember it? And then about 10% is stuff you've never seen before. So, anyway, things that help for recall is the repetition. I don't have a photographic memory like the Stanford Medical School dean, but you can still memorize a lot of stuff. And so this test we're going to have next week about the retest for the nomenclature is just, I'm just going to pick from the nomenclature problems that you had on this last test and on the old exam, and then just do it one more time. Okay. Try to recoup some points. Because if you can't do nomenclature, then in 1A, let's say because nomenclature is just one part of this class. So let's say you say, okay, I'm just going to skip the nomenclature part of this class. But if you go on to Chem 1A and you can't do nomenclature, then the instructor's not going to think you're going to pass the class. And they're going to have this bias, even though the other stuff you might be strong on. But if you're weak on nomenclature, then that's going to be a challenge. But anyway, we'll do it again and see how it goes. So just try to recall that. So going to this, even though this isn't the correct order here, we write it in this order. It's numerical order. So the largest numbers go at the end. And so we just go in numerical order all the way out. And that way, if an oxidizer comes along, it's going to pluck out the furthest electrons from it in terms of distance. Or in terms of the orbitals are bigger. The n equals 4 orbitals are bigger than n equals 3 orbitals. Yeah. So both of these are common. In fact, this is probably more common here. But we got to be careful because this is not how we fill it. This is how we fill it here. All right, so this would be for vanadium, which has 3d electrons. And so when we're looking at ionization energy, the first level that we want to understand it is the bigger the atom, the easier it is to steal the electron from. So the easiest atom will be francium or cesium. Francium or cesium are going to be the easiest, and therefore they're going to have the lowest ionization energy. Ionization energy is the amount of energy required to strip an electron off a gaseous atom. The hardest atom to strip an electron off will be helium. This will have the highest ionization energy.
Ionization energy is the amount of energy required to strip off an atom?
Yeah. And so for example, if we try to ionize helium, helium is normally a gas, so that's not a problem. But francium and cesium are not normally gases, so we'll do cesium here. What we have to do is, if it's normally a gas, no big deal, we'll do that. If it's a diatomic gas, we have to first break the bond. And so for something like hydrogen, what we have to do is we have to break the two atoms apart, and then we'll form atomic hydrogen. And then from atomic hydrogen, we just look at one of the hydrogen atoms because we're trying to ionize that. And so we're looking at atomic hydrogen losing electron. When atomic hydrogen loses an electron, it goes to H plus, and then the electron goes somewhere. When helium loses an electron, it goes to He plus an electron. Cesium loses, it goes to cesium plus an electron. And so helium's going to have the highest ionization energy. Cesium's going to have the lowest ionization energy. And then there are blips. These blips are important in Chem 1A. So for example, it turns out, what do you think is harder to ionize, a 3s or a 3p?
3s.
Yeah.
3.
Harder to ionize 3s, easier to ionize 3p. And so even though we go like this, what happens is this. Even though, what's 3s? At the end would be magnesium, and then 3p would be aluminum. So if we look at magnesium, and we look at aluminum, aluminum's smaller. Why? Because as we go across, what happens? The size shrinks. So that's the first thing. This is level 1. You have to remember what happens as we go across, the size shrinks. The next level is why. And so you don't want to do everything at once. You want to do step by step. So the first thing is understand this, be able to recall it. The next thing is, why is that? Well, a lot of people will go, I want to know the why because then that makes it easier to remember, which is fine. You could do it that way. But if you start feeling overwhelmed with this stuff, then just learn it at the base level. The base level, the size gets smaller. Now somebody tell me why it gets smaller.
Can it be more concentrated? Or is it getting closer to completing one shell?
That's not why.
Because the energy's or like it's more spread out.
Probably the easiest is to compare hydrogen. This is atomic hydrogen, not diatomic hydrogen, and helium. So if we look at a hydrogen atom versus a helium atom's smaller. Why?
It's harder to recover the energy that comes from it.
It's harder. That's why it has but that's a little bit circular, because if it's harder to take an electron, then it has a higher ionization energy. But why is it harder to take an electron off helium than hydrogen?
It's closer to
See,
shells completed.
I just talked about this yesterday, but how much information do you forget from yesterday? Lots. Yeah, it's like people have done studies about this, and it's about 60% of the information you lose. And so,
I think it's probably because of the highest occupied principal energy level. I think helium has a higher one, so it'd be a
no, they're the same. The principal energy, hydrogen and helium are both in the first shell.
Does it have to do with valence electrons?
It doesn't have to do with valence electrons. It has to do with protons, right. It has to do with the number of protons. Hydrogen has 1 proton and 1 electron. And so I drew this. If you're an electron, which one are you going to have a stronger attraction to?
Right.
The right. So if you're a bird, think about this. Maybe there's lots of food at the nest, so you don't want to go too far away. There's going to be an attraction there. And so this is going to keep the bird closer to the nucleus. Here, maybe it's not as strongly attracted. And if it's not as strongly attracted, then there's more probability. Remember, what was this called? What was this called?
The 99%. No. That's the border. Electron field?
Not the electron field. Kind of electron field, but something else. Electron. I also talked about this yesterday.
Probability field?
Cloud, electron cloud, and probability. We could call it a probability cloud too. But this one, the probability can be a little farther out. like this. This one, the probability is not going to be as spread out. This one, the probability is going to be more concentrated here because of Coulomb's law. It's going to pull it in closer. And therefore, when we look at the boundary, what was that boundary called? 95% boundary. When we draw the 95% boundary, the 95% boundary here on the hydrogen atom is much bigger than the 95% boundary on helium. Now you go, helium has 2 electrons, but the 2 electrons in one orbital try to stay away from each other. The 2 electrons try to stay away from each other because they're both negatively charged. So this electron has a straight shot to the nucleus. Once in a while, this electron will do something. It'll come in here between these two and do something called shielding or blocking. And so if the electron comes over here and shields it, then this electron's not going to see the full +2 charge. Rather, it's going to see about the +1 charge. Right? But shielding and blocking doesn't happen so frequently in the same shell. Shielding and blocking happens much more frequently if we're looking at an outer shell versus an inner shell here. And shielding and blocking are what causes this splitting. The reason we have this splitting here is because of shielding, this blocking that occurs with the electrons. It's much easier to shield a p orbital than it is to shield an s orbital from the nucleus. So this is why we see the splitting. But we don't need to know that. All we need to know is the just memorize this. Don't worry about what it, where it comes from. You can deal with where it comes from later. But right now, just take this step. And if you just take this step, then it's not that complicated. Well, it is. It's hard to memorize stuff for me, but it's not like you have to come up with reasons why the splitting occurs. And this is what happens with advanced classes. With advanced classes, then they'll start asking little questions. Oh, why is that? Why is it split? And if they've never talked about it, you have to come up with some kind of crafty explanation because maybe it's the first time you even thought of it. That's the advanced problem. And so, but the thing is, and this is how you can get better prepared for advanced problems. You get better prepared for advanced problems by getting the basics first. It's like, it's like these professional basketball players. You would think, these professional basketball players, they don't need to work on drills or fundamental stuff, or do they? In order to do all those tricky things that they do they need to have the basics down pretty well, would you say, or? No, and so the same thing in science, the same thing. If this is like easy, mindless, then your mind can drift onto different things. This is what they say, if you're just always worried about the basics. This is a very interesting documentary I watched about the Romans, and I'll try to summarize it, but it might not be 100% accurate. But this is what I got out of that documentary. Roman concrete is people are still studying Roman concrete because if you go to Home Depot and you buy concrete, is it as good of quality as that Roman concrete? No, it's not even. If you look at the concrete structures in LA, do you think those are going to last for centuries? No, they're going to fall apart. And so people are still studying the composition of Roman concrete because it turned out that, whatever they did, they got a really good mix of different components in their concrete, and it's been really long lasting and quite good. But they are talking about, how come they were able to make such significant advances versus other cultures? And then they started talking about, one of the reasons why they were able to make such significant advances is because they weren't spending all their time looking for food. The basics like survival. And they had more time to experiment and think about things. So if you aren't always searching for food, then you have more time to think about more advanced stuff. And I think the same thing here on exams. If you aren't just worried about the basic stuff, you know, just dealing with the simplest stuff, then there's no way you're going to get the more advanced stuff. But if you have the more advanced stuff pretty well down, that you don't have to use too much mind power to generate a diagram like this, then you can start thinking about little things, you know, little things that you might have not have thought of before. And so, so I thought that was good. And so for exams, you know, and everybody has to find their own, you know, what works for them, because I was told a lot of things when I was a student about how to study, but pretty much I just took bits and pieces, but nobody had a system that kind of worked for me. I had to figure out a system that worked for me. But if you don't have a system, then you know, you want to just use somebody else's system initially. All right, so what we'll do is, okay, first we learn, you know, the patterns, the trends. And so the trend is the size decreases as we go left to right. And so the radius decreases. And the size increases as we go, you know, from the top down. Why does the size decrease? The size decreases because we get more protons. But here, we get more protons as we go down. And so, for example, francium and cesium have a heck of a lot more protons than hydrogen. Why doesn't the size decrease? Yeah, it's because we're adding shells. And we're adding shells of orbitals. And you say, so what? We're adding shells. Well, the reason why adding shells increases the size is because the inner shells are very effective at blocking the charge from an outer shell. So if I'm in, let's say this is 1s, and then I go to the next shell, which is 2s, then these 1s electrons here are very good at blocking the charge. And so even though I might go +3 now in the nucleus with lithium, it's essentially a +1. And then this electron's further out, it's in a higher energy orbital, because these inner electrons block that. And so these are the types of things you might think about if you have time. And then this would be kind of at this level. You know, a lot of times what I found in the advanced class is, and this is what I did as a student, because I wanted to get the advanced or the challenge problems. And so as a student at UCLA, and it's harder now, or maybe it's easier now, but what had happened at UCLA is they used to have the books, and you go in the bookstore, and the bookstore had all the books for the classes. And so if I was taking this class, then I always looked at the next level of difficulty. So let's say I'm in this class, and the next harder class, I'd look up the number, and then I'd find the book. And then I'd start skimming that to look for what types of problems that they might ask. Because usually it's just something like, you know, like here in Chem 4, we don't talk about shielding in this. But let's say somebody asked you, like somebody wanted to challenge you as a Chem 4 student, what they do is they just take something from Chem 1A and ask you that, right? And so it's not that. So anyway, that, and then also exposure. Exposing yourself to as many problem-solving techniques as possible will build your toolbox. It'll build, I think, this neural network. You know, the more connections you can make, the easier it is to solve problems.
The inner shells are very effective at blocking the outer electrons?
Inner shell are very effective shielders. And so the total nuclear charge is 3. We call that Z. Z is equal to 3. However, this electron doesn't see +3. This on lithium doesn't, because these 2 inner shell electrons will cut it down. And so what we get is something called Z effective. Z effective is about 1. And so all of these atoms have a Z effective of about 1 because all the inner shell electrons will block the additional protons. And then we're just left with this outermost electron, which is pretty far away and gets farther and farther away. And there's not enough, even though cesium has how many protons? Cesium has a total of 55 protons. And so you think 55 protons versus 1. 55 is going to pull in that outermost electron very closely, but it doesn't. It doesn't because the inner shell electrons shield. And so effectively it's just saying +1 and it's already so far away. This is why cesium turns out that electron is very loosely held. It's very easy to ionize. Cesium's ionization energy is less than 500 kilojoules per mole, whereas helium's ionization energy is like 2,500 kilojoules per mole. And so we go from about 500 to 2,500 in terms of ionization energy. Then why is it here, the case? Well, the case here is when we go across the periodic table, it's the same shell. Same shell electrons are ineffective shielders. These two electrons are, not only are they in the same shell, they're in the same orbital, and they try to stay apart from each other, but once in a while it'll shield it. And so the shielding isn't so effective. So both of these electrons see essentially that +3 there. Not exactly, it's going to be lowered. They have some rules in physics about how much it's lowered by same shell electrons. These rules are called, these calculations, we can calculate the Z effective for any of the electrons here using an empirical equation, Slater's rule, it's called. All right, and so what we want to do is just understand this. Then once we get this down, then we might start thinking of something like magnesium. Which one's bigger, which one's smaller? So if we go to magnesium, aluminum, they're in the same shell. If they're in the same shell, then aluminum should be smaller because it has more protons. So aluminum has 13 protons, magnesium has 12 protons. And so this is +12, this is +13. And so we expect it to be smaller because the electrons are in the same shell and they kind of try to stay away from each other, and they aren't very effective at shielding or blocking, you know, the sunlight or whatever you want to think of, the nest or the nucleus. However, so if aluminum's smaller, then which one should be harder to ionize? Aluminum should be harder to ionize, but it turns out that aluminum is easier to ionize. So this would be a challenge question. This is an easy question in Chem 1A because we talk about it, that paragraph. But in Chem 4, this would be like a challenge problem. Well, it goes the same way, you know, as you go on in the courses just become progressively more difficult. You know, every quarter that I was at UCLA, I go, woo, you know, that was the hardest quarter I've ever had. And then the next quarter is even harder. And it just gets progressively harder and harder, and you think, when is it going to end? When is it going to get easier? Well, it doesn't get any easier until you graduate, and then it gets easy because you don't have to worry about classes anymore. But every successive quarter was like a lot harder than the previous. That's what I felt when I was a student. It just got harder and harder and harder. And so, but then I thought, you know, it's kind of the same thing. Like here, you know, obviously, if you're going to ask a Chem 1A, this is like a Chem 1A, this is a basic problem in Chem 1A. You ask a Chem 4 student, of course it's going to be hard. And so this is why I had that strategy of looking at that. But what's the reason for this? Well, yeah, we expect aluminum to have a higher ionization energy. So for example, if we go from sodium to magnesium, the ionization energy goes up. And we go from magnesium to aluminum, we expect the ionization energy to go up, correct? Because it's smaller. Sodium is bigger, magnesium is smaller, magnesium is going to be harder to ionize. Aluminum is smaller than magnesium, but aluminum is easier to ionize. Why is that? Why is that? And so in this particular case, we have to dig a little bit deeper. When we ionize magnesium, we're taking one of these 3s electrons. All these electrons are gone. However, when we ionize aluminum, we're taking not a 3s electron, we're taking one of the 3p, yeah, 310. Don't call it 310 because people won't know what you're talking about in quantum. Because they'll go, oh, that's a violation of the Schrodinger equation, 310. You would call it 310. Let's do a 310 plus 1/2. Well, it turns out that the p orbital electrons are easier to ionize than s. And why is that? Why that is because when we look at the probability distribution for p orbital, so let's say we have the plus x here in the nucleus. The p orbital probability distribution, the electron has a lower probability of being close to the nucleus. The p is this shape here. So what happens with a p electron is it has a different distribution than an s electron. The s electron has the greatest number of dots right next to the nucleus. When we look at a p, we have something called a node here. The node is a place where we have zero probability of finding the electron. And what happens is this. We say the s electron, even though this is a 3s electron, the 3s electron can get very close to the nucleus. 3s electron has all this volume, you know, and so it can get around a 1s electron. A 1s electron is going to be confined to this space, you know, here. A 2s electron will be confined to this space. A 3s electron has all this volume here, so it can sneak in through the 2s, it can sneak past the 1s and get very close to the nucleus. We call this penetration, and so a 3s electron can penetrate more closely to the nucleus, whereas a 3p electron can't penetrate as closely because it's better shielded. And so the inner electrons here tend to block the amount of nuclear charge this one sees, whereas this one's more penetrating, and so it doesn't get blocked as easily. And so that was, you don't have to worry about this. It showed a bunch of blips. I think he talks about the blips in the book, but we're not going to worry about it. This is more Chem 1A, and this is basic stuff for Chem 1A. And so what I want to just say is that there are going to be some exceptions. And so what we need to know is the smaller it is, the harder it is to ionize. And so when we go from magnesium to aluminum, it blips. But when we go from aluminum to what's next? Silicon, it's harder to ionize silicon. And then when we go from silicon to phosphorus, it's harder to ionize phosphorus. However, when we go from phosphorus to sulfur, sulfur's smaller. And we get another blip, another exception like this. Why is that? So when we try to ionize, let me erase some of these here. And so this is an exception. And so why do we have an exception? Sulfur is smaller than a phosphorus, and yet it's easier to ionize. That doesn't make sense. So sulfur is easier to ionize. Why is that? And so these are the problems that occur, like, you know, if nobody's ever talked about this, this was never in the homework, what would you do? Well, you know, you start trying to think, you know, what could that be? And so you look at other things to compare it. So for example, if you look at the orbital energy level diagram for phosphorus, it looks like this. If we look at the orbital energy diagram for sulfur, it has one more electron. Where does that one more electron go? In any of the p's, and it would have to be spin down. So we'll throw it here. And, um, and this is the reason why. When we ionize aluminum, silicon, phosphorus, we're just plugging one of the single electrons in the P. However, when we get to sulfur, we're ionizing a pair of electrons. So what's the difference? Well, when we have a pair of electrons, we have two negative charges in the single orbital. And there's something called electron-electron repulsion based on Coulomb's law. Coulomb's law says like charges attract or repel. Repel. So these are two like charges. So it gets crowded. And so if you have two electrons in the same orbital, then it's going to be easier to ionize. And so this is what causes this next blip here. This next blip is caused by ionizing a paired electron versus a single electron. But then we lose that because now we're just ionizing paired electrons, because when we go to oxygen, we're going to take one of these paired electrons here to ionize. Here. And so, oh, not oxygen, sorry. What comes after sulfur? Chlorine. When we go to chlorine, it goes like this. And then after chlorine, argon. And argon is going to be very difficult to ionize. Here. It is. In fact, all the noble gases are very difficult to ionize. And that makes them very unreactive. Here. All the metals are easy to ionize, especially the alkali metals. All the alkali metals are very easy to ionize because of their large size. But there's another thing that causes these to be very difficult to ionize, and that's because they have a filled shell electron configuration. And so in the next part of this chapter, they talk about successive ionization energies. So what we have is we have IE, this stands for ionization energy 1, 2, 3, etc. And so what we do is we do it one step at a time. So if we're looking at ionizing, let's say we're looking at ionizing aluminum, and we go from IE1, we'll form aluminum plus. But is aluminum plus the standard charge for aluminum? No. What is the charge on aluminum? 3 plus. So we'll need IE2. That gives us aluminum 3 plus. And then we'll go to IE3. Oh, 2 plus, sorry. This gives aluminum 2 plus. We'll go IE3. This gives us aluminum 3 plus. How about IE4? IE4 is too costly. When I say costly, it's too much energy. It's about 10 times the energy. It could happen, of course. It could happen. You could lose all the electrons if you have enough energy. You put this in the Large Hadron Collider, the electrons aren't going to survive, perhaps. There's lots of energy. But for chemistry, this is too costly. Why? Is IE4 too costly?
Wouldn't it make it unstable?
In one way, it would make it unstable. In another way, it'd make it more stable. Anyway, this diagram here, I forgot to write this is the ionization energy goes up. Remember I talked about aluminum oxide? Does anybody remember what I said about aluminum oxide? Maybe. I've had tests where the instructor just made the passing mention of something and most people ignored it, but it was on the exam. Aluminum oxide. Aluminum oxide has some of the strongest bonds. Why? It has extremely strong lattice. very high melting point. You can't melt this stuff. Its melting point is so high. Technically you could, but practically you can't. When I used to have to do stuff at very high temperature. I did a lot of high temperature stuff, and I would use aluminum oxide cookware. We call it alumina foam. You know, they make aluminum oxide goggles. Aluminum oxide is normally white, but if you get one single crystal of aluminum oxide, it's transparent. It's colorless. You can see right through it. And so these are made for like these nuclear bomber pilots. They have these aluminum oxide goggles. These aluminum oxide goggles, they dope with, dope means they put impurities in there. They put these impurities that when you apply an electric field to it, electric current, it completely blocks out all light. And so if there's some, what they're worried about is if there's some nuclear explosion, they'd go blind, right, by looking at the blast. And so they have these that will cut all the light out in, like, I don't know, microsecond or nanosecond or something like that, so that they wouldn't go permanently blind. And they're very tough. And so these are like things that you would make connections. This is like if you always take the same path, let's say to school, you start noticing little things, especially if things are different. Start noticing. But one of the things is we know Coulomb's law. So aluminum's 3 plus, oxide is 2 minus. So this is going to be a very strong bond, 3 plus and 2 minus. It's because of the high charge. Wouldn't it be better if it were 4 plus? Think about how much stronger that would be. If aluminum were 4 plus, we could make a much stronger bond, right, with oxide. So we should go for it. Yeah. We should try to make aluminum 4 plus, and then oxide, we'd have an even better nuclear bomber goggles, or we'd have even better cookware, because this cookware is not going, this would withstand even higher temperatures because it would be much stronger. But
Is that what the Romans did?
no, the Romans did this. The Romans cooked the calcium carbonate in kilns. They had coal, so they were able to cook the calcium carbonate to make calcium oxide and what's the other product for this? CO2. This is the Roman reaction. Some people rank that reaction in the top 10. I looked it up. It wasn't in the top 10 2 years ago or something like that. It was easily, I guess there are others that displaced it, but this is one of the big ones here. It's not just that the Romans had the free time to experiment, but the Romans also had resources, and one of the resources you need to do this is coal. So a lot of civilizations, they didn't have access to coal, and so they couldn't get these extreme temperatures that you need to conduct this reaction. This is just cooking limestone. So this would have an even stronger lattice. And so in the argument for stability, it's not necessarily, there's a trade-off, because each time you ionize this costs energy. It's not free. This costs energy. This costs energy. You're paying for this. You're paying for this. It's like taxes. I don't want to pay anymore. Let's just stay as aluminum. If you stay as aluminum, you don't have to pay anything, right? Because each ionization, it's not free. Even, what's the easiest element to ionize? No. The easiest element to ionize is CS, cesium, or francium. That's the easiest, but you know, it still costs money. Still costs under $500. Are you going to pay $500 so somebody can take your electron?
I'm good.
I wouldn't. I'd just say, I'm going to keep my electron. I don't want to pay $500. Right? I wouldn't. And then helium is going to cost you $25. Well, I'm definitely not going to pay $2,500. Right? I'm going to hold on to my electrons and not pay anybody. But everybody says cesium is the easiest and it's very reactive. It wants to lose that electron. Why does it want to lose that electron? You know why? Because cesium pays $500, but it gets a lot more in return. So let's say, okay, would you pay $500 if you got back $1,500? And then you'd say, yeah, that's a good investment. And so what we do is we create ions because we're going to get that energy back. Where do we get that energy back? When we form bonds. When we form bonds, we get that energy back. So you might invest $500, but you're going to get $1,500 back, so you're going to get $1,000. So would you pay $500 to get $1,000 back? Or $1,500 back? Yeah. You would do that, right? And so this is not stable. Aluminum 3+ is actually not stable. But that's where this is the most common charge for aluminum. The reason why we form aluminum 3+ is so we can form things like aluminum oxide, which are tremendously stable. And this is where you're going to get the money back. And so what we say is, yes, this is well worth the cost. I'm definitely going to invest this. I think this is going to be about 700, and then this is going to be about 1,400, and this is going to be about another 2,000. So the cost is adding up because each successive one grows. Each successive one is about double the previous one. And then the cost is getting higher and higher, and you're thinking, do you want to spend that much energy to get this? Yes. Why? Because we're going to form this. And then, so my question is, if that's the case, then why don't we go to aluminum 4+? Wouldn't aluminum 4+ be a heck of a lot better? Yes. Because if we could make this out of 4+ rather than 3+, it's going to make this even stronger. But the cost is 10 times. Cost is too much, and therefore it doesn't happen. And so what this boils down to is this. The cost to ionize valence electrons is reasonable. The cost to ionize core electrons is unreasonable. And so all this costs. And so what happens is chemistry happens with the valence electrons. And so Juarez has this very nice diagram over here. So here, if we look at the outermost shell, we have 3 valence electrons, 2 in the 3s and 1 in the 3p here. This is missing 3p. This has got the 3p there. And so the first electron we're going to ionize is a 3p. That's IE1. The second will be one of these paired. That's IE2 and then IE3. And so we've knocked out the valence shell. But now if we start trying to eat up the core, forget it. It's going to cost way too much energy. Now we're a lot closer to the nucleus. It's going to be a lot more difficult. And so the successive ionization energies for the valence are reasonable, but when we try to ionize the core, forget it. So here. Now, this core here is like neon, and so neon is very hard to ionize here. It'd be like neon. The other thing, metals, actually, since we're talking, so I'm just going to probably talk about ionization energy and one other thing here for chapter 11, and that is metals and nonmetals. If, on the other hand, we're like this, what element is this?
Including the 4s?
Yeah.
Including the 4s?
No, excluding the 4s, sorry.
Chlorine?
Chlorine. Chlorine, what do you think the cost is to lose, how many electrons will we have to lose? 1, 2, 3, 4, 5, 6, 7. So we'd have IE1 through IE7. The cost is going to be quite high, but it's possible. So plus 7 is 1, but it would probably be much easier to go minus 1. And that's called electron affinity. And so I need to talk about that, I think, next. Which we call EA. Electron affinity is, let's say I take a chlorine and then add an electron, I'll form chloride. This would be EA. EA are typically exothermic. At least EA1s. EA2s are not. IEs are typically endothermic. So IEs cost energy, electron affinities, we get energy back. So if somebody's going to give you $100, you go for it. So chlorine would do that. Here, chlorine's going to grab that electron. Oxygen wants how many electrons? 2. And so we're going to have EA1 and EA2. EA1 is exothermic. However, EA2 is endothermic. And combined, this whole process to go from oxygen to oxygen 2 minus is endothermic. EA1 plus EA2. So that costs energy, just like aluminum. And so why do that? If it's going to cost you energy, you're going up in energy, you're becoming less stable. Why would you do that? Why? You know, if I were oxygen, I'd say, oh, forget it. I'm going to stop at O minus 1 because I don't want to spend any money. But if you stop at O minus 1, is aluminum oxide going to be stronger or weaker? If you stop at O minus 1.
Probably weaker.
Weaker. And so if you stop at O minus 1, it's going to cost you less, for sure. In fact, you're going to get energy back. But the return is, is this still recording? The return isn't as great. And so what happens here is we're going to make a much stronger bond, twice as strong with O2 minus than O1 minus. And so even though this costs energy, the return is when we make something like aluminum oxide or any other oxide, copper oxide, copper 1 oxide, copper 2 oxide, it's going to be much stronger. Because the higher the charge, the stronger the bond. And so we're going to go there. But likewise, hey, wait a minute. I am going to do this. I want to go to O3 minus. This is not O3 ozone, but O3 with negative charge of minus 3. Excuse me, an oxygen atom with a minus 3 charge here. And I go, okay, this is going to make an even stronger bond, because if I could go plus 3 and minus 3, then the force is going to be around 9 times. Versus a plus 3 minus 2, the force is going to be around 6 times. Versus a plus 3 and a minus 1, the force is going to be around 3 times. So I go, wow, this is looking good. I'd rather have 9 times the force than 6 times the force, right? I'd much rather have that. And so I want to go for it. I'm going to go for oxygen with a 3 minus charge. Why doesn't that work? This is a very nice diagram. Thank you for writing it. So this would be the electron configuration for oxygen here. So O1 minus is, I'll put that extra electron in this 2p, there's room for it. That's O1 minus. And I get energy in return. But I don't want to stop at O1 minus because a +3 minus 1 bond isn't going to be as strong as a +3 minus 2. And so this is going to give me a lot more return. And so I'm going to go with an O2 minus. When I go to O2 minus, this is going to fill the second shell here. Okay, then it costs a little bit of energy because I'm putting 2 negative charges on there, but it's worth it because I get a stronger ionic bond. But I want to go even stronger, the ionic bond. I'm going to go to O3 minus. Is that going to happen? No, because where does that electron go? It's going to go in the next shell. If that electron goes in the next shell, is it going to be as stable? No, it's going to be a lot further out from the nucleus. And so this one costs too much energy.
Or you can add more, you can add 8 more.
It's hard to hold on.
Yeah.
It's like, you know, you only have enough hands. Although I was watching this YouTube about, was it Oktoberfest in Germany, and the waitress was carrying like, I don't know how many mugs of beer. It's crazy. It was like 25 mugs of beer or something in 2 hands. But, you know, atoms can't hold on to too many electrons. You know, they're all negatively charged. They're all kind of repelling each other. Well, it's too hard to hold on. And so the cost is too high because this is going in the next shell. And so EA1, you know, not everything just gains 1 electron, you know. But we just fill in the shells. So for example, nitrogen, you know, nitrogen would form nitride. What's the formula for nitride ion? It's not, you know, this always gets people because there's nitrate, there's nitrite, and there's nitride. What's the difference between those 3?
Nitrate has an oxygen.
Yeah.
Nitrate has -1 oxygen. Nitride is just the ion.
When you have the T, those are oxyanions. So nitrate is what? Nitrite and nitride and 3 minus. And so nitrogen is 2s2, 2p3, and then there's room for 3 electrons here. So we're going to just fill it up. That's it. Now, there's some funny stuff about this. Which element do you think wants the electron the most in the periodic? Do you think helium wants the electron the most? It should because it has the highest, you know, exposed nuclear charge maybe. But there's no room for it because if helium grabs an electron, it'd have to go in the next shell. Same thing with neon, argon, krypton. None of those want electrons. And so I said that the EA1 is less than 0. Here, I have to put a little asterisk here because EA1 is less than 0 for all the elements except for the noble gases. The noble gases don't want to lose and they don't want to gain, except the noble gases. The element that wants the electrons the most is the smallest one on the right side. This is going to be fluorine. Fluorine. So we expect fluorine to have the highest, the strongest. Highest, when we talk about energy, highest is tricky, you know, because it's not number scale high, like -10 versus +10. Which one's higher? In terms of energy, they're equal. because one's 10 below, the other's 10 above. They're equal in terms of energy, because energy is always positive, and the negative and the positive just refer to direction. And so when we say highest, we're either talking about the most negative or the most positive. And so which we expect fluorine to have the highest EA. But it doesn't. It turns out that chlorine has. This has the highest EA. And so expected versus observed. And so this would be a challenge problem. Why would you suspect that chlorine would have a higher EA? It's a lot bigger. And so it's not going to have as strong of a pull on the outermost electron. On the innermost electron, it has a strong pull. So for example, when we compare the inner electron, the 1s electron, so if I look at the 1s orbital on fluorine, its boundary is like this. Versus the 1s orbital on chlorine, the 1s orbital on chlorine has a much smaller boundary because chlorine has a lot more protons. And so it's going to pull the 1s electrons a lot closer. But the thing we're not looking at the inner, we're looking at the outermost. And so the electron's going to go into the outermost orbital. And the outermost orbital on chlorine is a lot bigger than the outermost orbital on fluorine. So we expect fluorine to have a higher EA, that is, it's going to want the electron more. But it doesn't. Chlorine does. And that's because of where the orbital goes. I mean, not where the orbital, what orbital the electron goes in. And so the electron would have to go into a 2p orbital here. Like for example, if this is spin up, this one will have to be spin down. Whereas in chlorine, the electron would go into a 3p orbital. So what we have is we have a situation where that this fluorine should have a stronger attraction but is less able to accommodate the electron. And so there's more room. Okay, if there's more room and chlorine has more space, then it's going to welcome a guest. And this guest electron will stay there. Whereas fluorine, it's a little bit cramped. And these two electrons might start annoying each other. If that's the case, then what about, what's fluorine, chlorine, what's next? Bromine. And therefore, would you expect bromine to have an even higher EA? Yeah, because it's going to be in the 4p orbital. And 4p orbital is luxurious. There's lots of space here. And so 4p orbital has plenty of space to accommodate that electron. And therefore, we would expect this to have an even higher EA. Now, higher, lower gets all mixed up. When I say higher electron affinity, it wants the electron. It wants to accommodate that electron. In terms of energies, we have to look at the numbers themselves to dictate that. But observed, it's lower. Why? So these are, again, these are like challenge problems. These are challenge problems because you haven't heard it before. I mean, obviously, if you know the answer, it's easy. You know, you go, oh yeah, that's easy. But if you haven't heard it before, then what do? And so you start digging into the basic stuff, you know, the drills or whatever you do. Can you think of a reason why?
They're going back to that because it's providing a lot of answers.
We might go back to that. That would be good. we start looking at the basics and see what we can figure out. But there's another reason why. And that is this. Fluorine is going to have the greatest attraction for the electron. If the electron goes in here, it's going to have the greatest attraction because Coulomb's law depends on the distance. And the closer it is, the stronger the attraction. Here. However, even though fluorine has the greatest attraction, it can't accommodate it because there's not as much room. So fluorine's like the person, they're very welcoming, but you're going to be cramped there. And so they come over anytime, stay in this room with this other electron. Chlorine is not going to be as welcoming. Chlorine might not want another guest as much as fluorine does. Fluorine really, really wants the guest to stay there in that room, but there's less space. Chlorine is going to have weaker attraction, distance, but more space.
It's because it has even weaker attraction than
Yeah.
fluorine.
But there's more space more than makes up for it, so the electron prefers to stay with chlorine, even though chlorine's not as welcoming as fluorine is. And so the electron prefers to stay with chlorine. However, there's plenty of space in bromine, but bromine is it going to be as welcoming? Is it going to be as strongly attracted to the electron?
You can lock the door.
No, it's not going to lock it. It's still going to want it. But here, when the electron goes here, it's not as connected to the nucleus. And so, in other words, bromine's lower. And so it's weird. Chlorine has the highest electron affinity out of all the elements.
Does that pattern continue with like iodine and
Yeah, iodine is going to be weaker. It's bigger. So we don't worry about that. And so most people think fluorine should have the strongest because it's the smallest and can want another electron, but it turns out it's chlorine. And so that's one of those exceptions. It's kind of weird. That's electron affinity.
what's the definition of electron affinity again?
It's the energy involved when an atom, gaseous atom, gains an electron. And we do it step by step, EA1, EA2, EA3. All right, and then I'm going to finish up the chapter by just looking at the periodic table. When we look at the periodic table, we divide it into metals, nonmetals, and semi-metals. So over here we have the metals. And so what is the definition of a metal?
Good conductor of electricity.
Conductor of electricity. Metals are good conductors of electricity. What else? Metals are typically malleable. Malleable means you can shape them into different shapes. Ductile means you can draw them into wire. And so if something conducts electricity, something's malleable and ductile, something has a metallic luster, that is, it kind of reflects light, and something that tends to lose electrons, then we call it a metal. That's the definition of a metal. Unfortunately, the definition of nonmetal is a lot more difficult because there are a lot of different nonmetals out there. Some nonmetals conduct electricity, some don't. And so nonmetals aren't so easy to define. But in terms of chemistry, we typically do it like this. Metals tend to lose electrons because when they're on the left side of the periodic table, it's easier to lose electrons. Over here, nonmetals tend to gain electrons. And so in terms of metals, things that lose electrons are reducers or oxidizers? Reducers. And the oxidizers will be over here, except the noble gases. The noble gases, they don't want to gain or lose.
What was the definition of a non-metal again?
Nonmetals are difficult because helium's a nonmetal, hydrogen's a nonmetal, but their properties are quite different. Metals, all the properties are similar. So metals are very easy to define. Nonmetals are a lot more difficult to define. But one characteristic they share is they tend to gain electrons, except for the noble gases. Noble gases are nonmetals that are quite stable. And so these tend to be oxidizers over here. We expect what do we expect the strongest reducer to be?
Strongest reducer?
Yeah. We'd expect it to be the one with the lowest ionization energy, which would be
Lithium?
not lithium,
CS.
cesium and francium. Cesium should be the best metal. Cesium should be the most conductive and the most reactive. Which should be the best non-metal?
Chlorine many times fluorine.
Fluorine, yeah.
But isn't chlorine better than fluorine? Because we said earlier.
What's that?
Isn't chlorine better than fluorine now?
For electron affinity.
Okay.
Yeah. The electron affinity, I'm not sure, it's that important, but there are just little exceptions here and there. The electron affinity, we're just talking about the exceptions. This is what I'm talking about these exceptions because these are more challenge type problems, but what you want to know is you just want to know the basics of it. And the basics are the electron affinity should increase as the size decreases. And so we should have increasing electron affinity this way. We should have increasing ionization energy this way. And we should have decreasing size this way. And if we go the opposite way, we flip them.
Increasing electrical energy. Sorry.
Electron affinity,
The second one is
ionization energy. Last one is size. This is the general pattern, and the little blips in the general pattern we could try to understand as more challenge problems. But if you're getting confused with all the blips and that kind of stuff, then you should know the basic pattern. The basic pattern will get you through most of this stuff. The thing is, a lot of people will get overwhelmed by trying to remember everything. And so best is just taking steps. All right. I had all that technical difficulty, so that's why I went on a little bit longer here. So let's take a break now. And then all right, the electron affinity stuff isn't in chapter 11, but it's more in chapter 12, but it's not formally talked about just yet. Well, one thing that's talked about in chapter 11 are the valence electrons, and so we're going to go on to chapter 12 now. Chapter 12 talks about bonding, and I already started talking about bonding. For example, aluminum oxide, forming the bonds there. And so what types of bonds are there? Can somebody recall the types of bonds that we have? Yeah, we have ionic bonds.
Covalent.
We have covalent bonds. Ionic bond is the bond between charged ions, charged atoms. Covalent bond is we have sharing, so sharing of electrons. It's covalent bond. What other types of bonds are there? The other type of bond is a metallic bond. In a metallic bond, the valence electron is just spread out like the ocean. Let's see. And so the first thing we're going to look at are ionic bonds. And, let's look at the ionic bond in aluminum oxide. That's one of the strongest ionic bonds out there. Aluminum oxide has different names for it. One of the names is alumina. So when I bought my ceramics, I bought alumina ceramics. Alumina ceramics can withstand extreme temperatures. And alumina or carborundum. If you look at sandpaper, most sandpaper, aluminum oxide is not that expensive. And on the Mohs hardness scale, it's a 9. And it's very strong. Like salt, you wouldn't make sandpaper out of table salt, just crush so easily. But with aluminum oxide, you can make good sandpaper. Diamond would make better sandpaper because diamond, do you know what the hardness is of diamond on the Mohs hardness scale? A 10. Is there anything higher than a 10? On the hardness scale, it turns out there are, but there are other restrictions to
Isn't
this.
graphite stronger than diamond, well, on one side?
No. Diamond is going to be strong. Diamond, the graphite, you're right, graphite is what we call anisotropic, and so its properties depend on which side you're looking at. But diamond's isotropic, it doesn't depend on which side you're looking at. The things that are harder than the diamond on the Mohs are anisotropic. And so on one side they might be 11, but on the other side they're less than 10. And so they're very directional, so you have to make sure the correct direction's pointed, otherwise they aren't going to be as hard. And so that's just one of the disadvantages. But aluminum has how many valence electrons? So when we go back over here, aluminum has 1, 2, 3 valence electrons. And these 3 valence electrons, I have a pair of electrons in the 3s and a single electron in one of the 3 p's. The way we're going to do it is, let's look at the formation. So what we're going to do is we're going to take aluminum plus oxygen to make aluminum oxide. And to make life simpler, what I'm going to do is I'm going to do atomic oxygen rather than, obviously it's molecular oxygen that does this. And so if I make aluminum oxide, I'd have to balance this. What would the balance be here? 2 aluminums and 3 oxygens, but I have 2 oxygens here. How can I get 3? I multiply it by 3 halves. So that gives me 3 oxygens. So what I'm going to do is I'm going to do this differently. I'm going to take my 2 aluminums like this, and I'm going to break apart the oxygen-oxygen bond. And so when I break it apart, I'm going to get 3 individual oxygens. Now the aluminums have 3 valence electrons, and we're going to show this as 3 dots, like this. Now I have a pair here and a single, but when I do it, I'm just going to write 3 single dots like this. And so this is what we call a Lewis dot symbol, or a Lewis symbol. We'll call it Lewis dot symbol. In a Lewis dot symbol, we just show it with 3 dots like this. So, looking at Lewis dot symbols, or Lewis symbols for short, I have an atom. If there's only 1 valence electron, I draw 1 dot. If there are 2 valence electrons, I usually draw a pair of dots like this. If there are 3 valence electrons, we usually draw 3 singles rather than 1 pair and 1 single, even though when I look at the energy level diagram, it's a pair and a single. This is just convention. People follow convention. What happens if I have 4? Well, if I have 4 valence electrons, then that means I have 1 pair in the 3s and then 2 singles. This would be like silicon. But what I'm going to do is I'm going to put 4 singles. Yeah, like this. If I have 5, then what I'm going to do is I divide the space around the atom into 4 regions. So I'm going to have a pair. So I'm going to have 1 pair and 3 singles. Like this. It's 5 valence electrons. If I have 6 valence electrons, then how many pairs will I have? Yeah, I'm going to have 2 pairs in any one of the 4 regions. I divide the region around the atom into 4 regions. And so it could be the top, bottom, left, or right. And so it doesn't matter where you put the 2 pairs. You can put them in any region you want. If I have 7 valence electrons, I'm going to have 3 pairs. This and 1 single. And again, you could write it anywhere. So the single could occupy the bottom, top, right, or left position. And if I have 8 valence electrons, then
They're all filled up.
yeah, then it's all filled up. Everything's paired. So this would be 8 valence electrons, which would be like argon in this case. And so these are the Lewis symbols that we have. And so aluminum has 3 valence electrons. I'm going to write in 3 singles. Oxygen has how many valence electrons?
2.
No, not 2. Oxygen is 6, yeah. Oxygen is going to look like this, where we have 2 from the 2s and then 4 from the 2p. So I'll write it like this. When I look at oxygen, what does oxygen want to do?
Wants to gain electrons.
Okay, it has two choices. One choice is it can gain 2 electrons. The other choice it can lose 6. So the standard oxidation state, what we call, varies from +6 to -2. But what would be the easiest? -2. So it's oxygen's an oxidizer.
You have 9 valence electrons.
Could you have 9 valence electrons? No.
It's a show, right?
Yeah. Even if we have a lot more, look at the 4th shell. This is why we had to define valence electrons oddly, because in the 4th shell, how many electrons can we have? We can have 2, 4, 6, 8, 10, 12, 14, 16, 18. So aren't there 18 valence electrons in the 4th shell? It turns out there aren't. How many valence electrons in the 4th shell? Max? 8.
Octet rule, right?
Yeah, the octet rule, 2, 4, 6, 8. And that's because of the way we define valence electrons. Valence electrons are defined as the highest,
Shell.
not highest shell, highest
And value.
N value. That's what I wrote on the board. Highest N value. The highest N value is 4. And the max there is 8. Therefore, we have the octet rule. The Ds, even if they're filled or not filled, are considered inner electrons, not outer electrons. In the octet rule, the chemistry happens on the outer fringes of the atom. You know, the core electrons don't participate in chemical reactions. So the easiest thing to do for oxygen is to take 2 electrons. And is aluminum hard to take from? No, metals have low ionization energy. And so aluminum is going to be the victim of oxygen. So they write the arrows differently. I look at the oxygen as attacking aluminum and taking 1 electron there. Oxygen wants 2. So it'll take those 2. But aluminum can give up how many? Aluminum can give up 3. So I'm going to label these electrons maybe like this. So aluminum is going to lose all its valence electrons. Well, that's okay, as we talked about earlier. And when aluminum loses all, it's going to end up with a 3+ charge. And then oxygen is going to take those electrons, which you'll see. And so it's going to gain 2 electrons from the aluminum here. This. And that's going to give it a charge of -2. And what holds these together is the ionic bond. Ionic bond. Ionic bond is the charge between a +3 ion, +3 ion, and a -2 ion. Anions are bigger than cations. In general. And so the size trend flips, usually. The biggest ions are on the right side because those gain electrons. As we gain electrons, they get bigger and bigger. And as we lose electrons, they get smaller and smaller. So the size trend flips for ions. The biggest atoms are on the left side, the biggest ions are on the right side, which we'll talk about later. Not only do we form 1 ionic bond, but we form more. And so we're going to have another aluminum here. In fact, we form a lot. Of ionic bonds. And so what we end up with is what we call what do we call this? Lattice. And so we just extend this, etc., in 3 dimensions, and we build up a bigger and bigger crystal. So this is crystal lattice with lots of ionic bonds. we talked about this. If you have a +3 ball, then this +3 ball doesn't just want one -2 ball, it wants as many -2 balls as can fit. And if we have a -2 ball, we want as many +3 balls as can fit. Not just one, but as many as possible. And we start to build up the ionic lattice structure. So we call this is called a Lewis structure, because we're using these Lewis symbols to represent everything. So this is the Lewis structure for an ionic compound. Oxygen wants 2 electrons. However, it depends on who it takes. Metals are easy to oxidize because they have low ionization energies. But nonmetals are a lot harder to oxidize because they get smaller and smaller as you go to the right, and they become harder and harder to ionize. So what happens is this. Carbon has how many valence electrons? 4. And we write them like this. And then oxygen wants how many electrons?
2 or 6. Oh, it wants 2.
2. So let's say 2 oxygens attack carbon. So 2 oxygens try to oxidize carbon. And what forms? What's going to happen is each oxygen wants 2, so it'll take these 2 here, and then there's 2 left over, so another oxygen can come and take 2, and we have that. But there's a problem. As we move further and further right, what happens to ionization energy? It gets harder and harder to ionize. And so do you know what? Carbon's not going to let go of those electrons. Aluminum lets go of the electrons. So aluminum just loses it. Carbon hangs on to electrons. And what results is something like this, where carbon can't completely lose it. In other words, oxygen can't completely strip the electrons off carbon. And we end up with a situation like this. Now, what we want is we want an octet. We want an octet because, that's the greatest cost versus benefit when we get octets. And so there are different ways to get an octet. So for example, here, oxygen gets an octet by taking the electrons. Here, oxygen's going to get an octet by not taking the electrons. Oxygen's going to get an octet by sharing the electrons. So that's what we call an octet. This is an octet here. But carbon doesn't give up the electrons. Carbon's going to maintain an octet here. So if we look at the electrons around carbon, it looks like this. This is an octet. And so what we end up forming is covalent bonds. Covalent bonds are a result of sharing electrons here. So we end up showing it like this. Here, where we form double bonds. Each pair of electrons that are shared is considered one bond. So if I have 2 pairs, that's a double bond. 3 pairs would be a triple bond. So we end up with CO2. This is the Lewis structure of CO2. And oxygen isn't strong enough to completely oxidize carbon. That is, completely take the electrons. Here. We can look at another example. Let's say oxygen wants 2 electrons. and there's another oxygen that wants 2 electrons. And so both of these oxygens want the same thing, and it turns out this is a win-win situation. In this win-win situation, what they can do is they can attack one another like this to try to take the electrons. And what ends up happening is we form an octet by sharing the electrons here. And so this is the Lewis structure for a molecule. Structure. This one too. This is a Lewis structure. Carbon can do the same thing, except rather than forming molecules, you know what carbon does? It forms a lattice. But it's a different type of lattice. So if we have 2 carbons here, they don't end up sharing 4 and 4. They end up sharing 1 and 1. So this carbon wants 1, this carbon wants 1, they share it there. And so we end up with a situation like this, but then there's another carbon here, and then there's another carbon here, and another carbon here. And then this goes on. And so carbon doesn't form a single molecule like this. Instead, carbon forms a lattice. This is called a covalent lattice. And this covalent lattice can go on for 3 dimensions here. And this particular covalent lattice would be a diamond. Here. And so we use these Lewis symbols to generate Lewis structures for ionic compounds, which there's no sharing. We just create ions and we generate an ionic lattice. Or we use these Lewis symbols here to generate covalent structures. It could either be molecular or a covalent lattice like this, which would extend off in 3 dimensions. Okay. I forgot to record that, but just write that up here. So I gave you more information than what was in the problem. If you recall, when we had 2 unknown problems, I gave you 2 methods to solve them. What were the 2 methods that you could use to solve these? The 2 methods were either algebraically with a system of equations, 2 equations, 2 unknowns, or graphically with the graph. I did it graphically because I like that. This particular problem is a lot easier than the one that I did in class. It's a lot easier because the one I did in class, both reactants reacted. This one's a lot easier because A reacts but B doesn't react. In Chem 1A, you're going to get problems where A and B react. And that makes it much more difficult. That's like the problem I did in class. So the more exposure you get to these variations of, let's say, 2 unknown type problems, the easier it is to come up with a strategy to solve them. And so this one's a really easy one. Compared to Chapter 1 in Chem 1A. Chapter 1 in Chem 1A has some much harder ones.
That for us will be 35.5.
35.45. So let me give you the masses here. Sodium is 2299. Chlorine is 35.45. Nitrogen is what? Probably already have this memorized. What is it?
14.01.
14.01. Good. Oxygen is super easy to memorize. 16.00. Yeah.
This was
Chapter
chapter 10.
10, number 87.
What about silver?
Silver is 143. 107.87. 107.87. 107.87. Symbol for silver is Ag. 107.87. What's the charge on silver? +1. I don't know. There's always about 5 people who always tell me that silver is +2 every year. You know, I get about 5 people. Silver, remember, is not +2. Silver is always +1. All right, so we're going to do the next level of difficulty. Potassium chloride, will it react with silver nitrate?
Yeah.
Yes. And what does it form?
KNO3, AgCl.
An
Solid.
AgCl
The driving force.
solid. All right, now let's see, how many grams was it precipitated before?
2.0.
Okay, let's say 1.983 grams of silver chloride precipitated. Can you tell me the percentage of sodium chloride and potassium chloride in the mixture? Is it possible to deconvolute it?
Yeah.
It is. So this is what you do. Like when you're preparing for tests that are going to have a challenge problem. Depends on, you know, like I said, as you go on and get to next higher, they like to put more challenging problems on the test. And so what you do is you have this like the basic, you know, this 2 unknown problem kind of mastered, and then you start thinking, you know, what additional twist. So this is like the 2 unknown problem I did in class. The 2 unknown problem I did in class, I don't know if anybody remembers that, but does somebody remember it? I did a 2 unknown problem where we could either do it graphically or we could do it algebraically. And I said algebraically is going to be too much work. I'd rather do it graphically. And so I did it graphically. This one you could do graphically as well. So what you can do is you can apply the same algebra that I used for the 2 unknown problem, which was a totally different problem than this. But it's the exact same math. And so you could apply it to this. And so these are other types of things that you notice is if you have that other 2 unknown problem, then you'd say, oh, this is just the same thing. It's just a different problem.
Would potassium be 39.1?
Yeah. Potassium is going to be 39.1, or no, 10. Potassium is 39.10.
Are we writing this one down?
Yeah. I mean, if you're still working on the first one, just try to finish the first one. You know, what you want to do is you want to be able to do at least that basic one, but if you want to get to a more advanced one, you might try this one. 39.10. Oh yeah, okay, let me give you another card. So, but the problem is you know, let's say you're trying to get all of them, you know, the hard ones and the basic ones. It's too much. You know, you start with mastering the simple ones and then you move on to the higher ones. Higher level ones,
When we're finding the percentage, are we finding for KCl, are we finding, is it 1.624?
Yeah.
I gotcha.
Right. If you need another card, I have one too.